Hello, my name is Kyle Champley, and today I'm going to talk to you about a piece of software that me and some others have been working on for a little over 6 years. It's called Livermore Tomography Tools, and it's for accurate, fast, and flexible software solution for data processing and reconstruction. So the toolbox has a lot of different applications in computed tomography, or CT as I'll call it. And CT enables non-destructive or non-invasive, as they say in medical imaging, 3D imaging with applications in healthcare, security, and industrial imaging. So probably the one that people are most aware of is in medical imaging. So sometimes people know this as a CAT scan. And these things exist at pretty much every hospital, at least in the United States, and it has virtually eliminated exploratory surgery. Another application space of CT is airport luggage security. So again, every airport in, well, not every airport, most airports, your checked luggage goes through a full X-ray CT looking for explosives and other contraband. And soon in the United States, all your carry-on luggage will go through an X-ray CT. So currently, carry-on luggage is just a 2-projection X-ray, but they're moving on to full CT. And then another application is in industrial manufacturing. So this is anytime you're constructing some complex industrial part that you need quality control on. CT is a really good metrology tool. So one of the things that comes to mind is the field of additive manufacturing, or sometimes known as 3D printing. Especially when you're printing metals, it's very difficult, and you want to know that it's printing as you thought it were. So I feel very confident in saying that LTT exceeds the competition in its flexibility, accuracy, and its breadth of functionality. So this is sort of one slide that, in a nutshell, that describes LTT. So LTT, Livermore Tomography Tools, can process CT data from any scanner geometry, whether it be parallel beam, fan beam, cone beam, or fixed gantry. And just so you know, parallel beam is what they use at synchrotrons. Cone beam is the most common form of X-ray CT. That's where all the medical vendors are doing and so on. And then fixed gantry, that's sort of taking hold in industry and in airport security. And it's great because there's no moving parts. But they're also very weird geometries. But LTT enables you lots of flexibility to specify where all your sources and detectors are. So you're never limited by the geometry and what LTT can process. And it runs on any operating system, the major ones, Windows, Mac, and Linux, and any GPU hardware vendor. That's NVIDIA chips, AMD chips, Intel chips, and all processed with exceptional accuracy with specified units in a timely manner. Now what we mean by that is, in a timely manner, it's very fast. It's amongst the fastest of the packages out there. And what we mean by exceptional accuracy in specified units is, in the history of CT, it's been more of a qualitative tool, where you'd say, hey, I got an image, the bright spots are denser than the darker spots. And so you can only really assess things qualitatively versus what other parts of the images look like. But LTT is unique in that in every stage of the processing, the units are tracked. And so when we reconstruct something, we say, you know, this is your reconstruction in units of mass density, grams per centimeters cubed, something like that. And so what this does for you is you can go beyond qualitative, and you can go to think that quantitative, like material characterization. Like you could say, this is iron at 90% theoretical maximum density. But to do that, it involves a lot of modeling and physics that you need to put into it. In addition to that, LTT has a lot of state-of-the-art and novel algorithms that enable you to do things that you couldn't normally do before. So this slide here, I'm going to show you a 3D rendering of a 3D reconstruction that we've done with LTT. This is collaboration with the Army Research Laboratory, where they're studying how, they're doing research on armors. And so they're shooting projectiles through the armors and seeing how the armors react. Now you can't do this with optical photography because there's dust and debris everywhere. You can't see inside. In addition to that, not only can X-rays see through the debris, they can see inside the objects. So like I said, oh, and one other thing I wanted to mention is typical CT, you're taking around 1,000-ish projections, and this is a reconstruction with only 5, so it's definitely a very unique capability. And this is with flash x-rays. So I'm playing the movie now. You can see the bullet rotate around, and you can see the hole in the armor plate. And you see the front there, the far right, that is the core of the bullet, and the thing behind it flying off, that's the jacket that's being stripped off the bullet. Another unique capability of LTT is its physics-based reconstructions, and it will offer very superior image quality compared to other packages out there. So here I'm trying to illustrate why you would need this. So here, this is a reconstruction of a metal 3D printed truss, and on the left you have a standard reconstruction, on the right the LTT's physics-based reconstruction. The arrow's pointing to a dark spot in the center of a node. And you can see all the nodes there have dark, they're darker there. So the question is this real or not? Well, with this picture, you wouldn't know, because it's actually believable that these things would have density dropouts at the nodes, because as the trusses cool, they pull apart from each other. So they wanted to know, hey, do we really have density drops at the nodes? Well, applying our physics-based correction, we would say no. Because you can see now on the image on the right, there are no density dropouts. So this next slide just shows a zoom in of the images on the previous. So again, on the left, standard reconstruction, on the right, LTT physics-based reconstruction. So you can see that major node there in the center of the image on the left, it's dark, LTT, it's fixed up. But also notice that there are some density drops that are real. So notice that if you look at that main center of the node drop out, and look down into the right, you'll see another little dark spot. Well, that shows up both on LTT's reconstruction and the standard. So you can't just say every dropout is an artifact. But what LTT offers you here with the physics-based correction is which ones are real, which ones are not. So LTT is reliable, stable, and robust. Like I've said, development has been going on for over 6 years. It's at TRL level 7. It's used by over 50 staff here at Livermore. And executables have been distributed to 15 outside institutions under a government use-only license. In addition, it has been used to process data on more than 20 different CT systems and process thousands of data sets. So this is sort of evidence that it is stable, it is robust, it is reliably reconstructing with multiple users, multiple scanners over a long time. We also argue that it's very easy to use. So you can use it on the command line version where you type in very specific commands line by line, or as scripting, but for the common user, we offer you a graphical user interface where it easily guides you through the process of processing your data. You just click next, next, next. And it also enables you to view data in different orientations and analyze the numbers coming out, perform some 3D rendering, things like that. And it also comes with full help menus. You get, if you hover over any parameter, it'll tell you what it means. Then you have long descriptions of every algorithm telling you exactly what you're doing. So there is no black boxes here. Everybody gets to know exactly what's going on. And it was really developed in a, I would say, a professional software manner. The next part of the presentation is going to deal with a few areas that we think are potential applications where one could use LTT. The first one we'll talk about is medical imaging. So in medical imaging, what could you use LTT for that you can't do with current methods? So first of all, you could do quantitative assessment of disease progress. So for instance, if you went in for a scan for something, and then that hospital bought a new CT scanner, or you decided to go to a different hospital for a CT scan, well, they wouldn't be able to compare results from those two different CT systems, because CT systems reconstruct into arbitrary units that you don't know what they are, and so they can't monitor the growth of your tumor or the progression of osteoporosis, things like that. But because LTT is quantitatively accurate, you could reconstruct all this data into a common set of units and really be able to perform these longitudinal studies. The other thing that we thought would be good for medical imaging is because it's so flexible, it will allow CT vendors to quickly prototype new geometries that they feel might perform certain imaging tasks better. As an example of the quantitative accuracy, I have some plots at the bottom of this slide. And this is data for dual energy CT. So you take out a scanner and you scan an object at 2 different X-ray energy settings, and then you put them on a plot. And here we scanned a couple of materials like water, graphite, Teflon, magnesium, and we're putting scatter plots of just different CT scanners. And you see they're all over the place. They all overlap. Well, if you use what we call our SIRS processing, you get these really tight clusters that you can see on the right plot. And we've demonstrated that the accuracy and precision is over 98% on 11 different systems. These all have different sources, different detectors, different geometries. But this shows you that we really can accurately and precisely reconstruct the same units each time. And also notice the plot on the right, the units are quantitative. The x-axis is electron density. It's moles of electrons per centimeters cubed. And the y-axis is effective atomic number. Now these are real material quantities. Another application space would be airport luggage security. So in the past, the way it's worked is vendors provide the equipment and the software, and then they sell these to TSA to run at the airports. And they sell them under a maintenance contract where they'll come and calibrate the scanner every once in a while. But TSA and DHS were sort of frustrated with the speed at which new technologies were coming on the market. So what they decided to do was open up this middle step, which is the software processing, to third-party vendors. And they do this through what's called the Open Threat Assessment Program, or OTAP. And so they're basically saying that now anybody can write software to run on a certain vendor's equipment, and it can be done through purchase. So we know one company that was successful in this. The company is called Stradivan, and they're in Davis, California. And their part of the software chain was the part that looks at the CT images and says whether it thinks this is an explosive or not. Well, we think LTT would fit very nicely in this framework because of its flexibility, because it's not tied to a specific geometry, that we could easily fit in this third-party software space. Another application, as I said before, is industrial manufacturing. And one way that we could help in this, besides some of the ones I've shown earlier, is this. So typical industrial CT data collection could take several hours to scan one part. So this obviously is very expensive. And this is because you're taking like 1,000 projections of an object. And we have novel few-view CT reconstruction algorithms that are covered under an accepted patent application that are in LTT that enable similar image quality that you'd get, but you can take 10 times or even fewer X-ray projections. Now this does depend on the type of object that you're imaging, but for many industrial applications you really can do this. Now here's a demonstration of the technology. So on the left you see a reconstruction of a 180 micrometer diameter glass fiber. And this is a state-of-the-art reconstruction. So already what you're seeing there on the left is better than you could get out of almost any CT software package out there on the market. The other ones will look much, much worse than this. Now with LTT, we can go even further than that, and that's the next image over. You can see it's much cleaner, but that's not really the point. Oftentimes, people try to sell you on how good their algorithms work because they give examples by saying, hey, look how much cleaner the image looks. Well, cleaning an image is easy, but extracting more information out of the image is really the key, and we believe that we've done this here. And we're showing this to you by, we blow up the center part of that glass fiber, and that's the image furthest on the right, and you see it has a bright center. So after we imaged this thing, we didn't know it at the time, the manufacturer told us, yeah, in fact, the core of this glass fiber was germanium doped. And so there is a bright density spot at the center of this glass fiber. Now that's very obvious from the LTT reconstruction, but even in the state-of-the-art reconstruction, there's no way you could ever tell that existed. So there is more information that you're getting out of our our few view reconstruction algorithms. Another sort of a common thing that an algorithm that has been developed over many years is what they call metal artifact reduction. And it's basically that when you image metals next to like soft tissue of a body or plastic parts, it causes these streaking artifacts that really diminish the diagnostic quality of the image. But like I said, you know, conventional X-ray CT is like 1,000 projections. So what we've been able to do is combine metal artifact reduction with few view CT to get these sort of results here. So on the left, we have a state-of-the-art method. That's state-of-the-art for few view. So it is getting rid of a lot of the streaks, but then you have the LTT reconstruction on the right, where we're combining our novel algorithms of both metal artifact reduction and few view CT. So the last area of application that we'll talk about today is the academic and research sector. So we've already gotten a lot of interest in LTT in this area, and it's mostly because LTT offers access to state-of-the-art algorithms to the common user. That commercial and open source packages rarely offer such algorithms. And the reason why the academic and research sector is interested in this is for two reasons. One, they're inventing algorithms, they want to compare them versus other state-of-the-art. And the other reason is they have very challenging imaging problems, and they need the very best tools to be able to complete the science that they were tasked to do. So these are two reasons they would really be interested in LTT. The other reason is because LTT, the API of LTT, we provide bindings to Python, MATLAB, or any C, C++ application. And the API covers anything. So anything that you can run through the console application or the GUI application, you can also run through these bindings. So this is great because you can do fully customizable scripting with LTT, where users can use it as a library in their Python programs or their MATLAB or whatever they wish. So the last thing is, I made that claim that it far exceeds the competition, but I wanted to delve a little deeper into how it does that. So here I'm comparing it versus some general purpose CT reconstruction software packages. So it's not included on here, as I'm saying general purpose, so I'm not including software that like it's for, you know, North Star imaging or General Electric, because it only operates on their hardware. So what do we like versus the general purpose software? So in a few categories, so first, GPU processing. Oh wait, I wanted to go back. So I'm comparing this versus two open source packages, Astra and Conrad. Astra is, the A is for Antwerp, and Conrad was developed at Stanford University. And then the next one is Octopus Reconstruction, which is a commercial package, and then finally LTT. So first, GPU processing, they all have that. Next one, platform independence. Well, I marked Astra and Octopus as red because they have many limitations. Astra does not work on Mac, and Astra only works on NVIDIA chips. Octopus only works on Windows and NVIDIA chips, so no AMDs. The next category, flexible CT geometry. LTT is the only one that offers what I would say practical geometries. I think Astra, for instance, is a very academic exercise where the geometries they support are very rigid. Everything has to be perfectly centered, like your detector has to be perfectly centered in your field of view. And in practice, that never happens. So actually painting it yellow was perhaps a generous thing. The next one, modern algorithms. So some of these packages are doing okay. They have some algorithms in it. I would say they're a bit dated, but they do have some, for instance, iterative reconstruction algorithms, but they don't near compare to what LTT can do. The next one is large data sets. I painted these all yellow, but LTT, and this is the reason why. So in LTT, you're never limited by how much RAM you have on your GPU or your CPU. It will automatically, behind the scenes, divide things into digestible chunks so that you're never limited by your hardware. I could reconstruct a huge data set on my laptop if I wish. And keep in mind that CT data sets can range from sort of 20 gigabytes to a terabyte in size. Next one, quantitative accuracy. None of these are really quantitative tools but LTT. The next category, a GUI. Well, Astra and Conrad don't have GUIs, but Octopus and LTT does. I would comment that Octopus's GUI is very nice. And then last, volume rendering. So only Octopus and LTT offer volume rendering. And neither of them are that great. But I wanted to make a point here that LTT is for processing and reconstructing CT data. It is not for, it's not really designed for data visualization. So although we do offer some volume rendering, we keep it at a minimum because that space is filled with a lot of great software that already exists that we would never even want to compete with. So like I said, we do offer a little bit, but that's just because it is nice to see as you're processing the data what volume renderings look like. But if you really want the professional stuff, you just go off to another package. So thank you for listening today. If you have any further interest in LTT, feel free to send me an email. Thank you.